We're going to do some more counting. Counting is hard, as we mentioned in the first video, and we're going to worry here about sort of extending and practicing the counting, and then adding a couple of observations about counting. Okay, so item number one is probability. An awful lot of elementary probability is just a question of counting, and you sort of write down a fraction where the top of the fraction is the number of cases you're interested in, and the bottom of the fraction is the total number of possible cases. So I'm going to do, for example, poker hands, and so I'll start by observing that the total number of poker hands is 52, choose 5. There are 52 cards in the deck. You dealt 5, order doesn't matter. You don't need to know much about poker. Most folks, in my experience, know enough to get by with the counting. Okay, so poker is dealt in 5 cards hands. Certain hands are worth more basically because they're less likely, and when you're dealt, the order doesn't matter. So we'll take ace to be high. If that doesn't mean anything to you, don't worry about it. Okay, so an example, a royal straight flush consists of the 5 highest cards, all the same suit. So the 5 highest of spades, the 5 highest of diamonds, the 5 highest of clubs, or the 5 highest of hearts. Okay, so there's only only 4 royal flush straights. So the total number of hands that are of interest is 4. The total number of hands being dealt at all is 52, choose 5. So the basic probability of being dealt a royal straight flush is 4 divided by 52, choose 5. Let's get some idea what that looks like. I'll pop up the command line again and ask for Sage, and I'll say here, let's see, 4 divided by, and the way you say 52, choose 5 is you say binomial, 52, 5. Okay, and now Sage, like any good algebra system, only gives you a fraction for that. It doesn't actually evaluate it. So the way you ask to evaluate it is you say .n, which means something like numerical. And it tells you it's the part at the beginning doesn't really matter. Can you see the 10 to the minus 6? So it's very small chance of being dealt a royal straight flush. A flush consists of 5 cards that are all the same suit. We saw that with a royal straight flush, but in this case, it consists of 5 cards that are not necessarily the top 5 cards, all the same suit. So the chance of a flush in hearts is you have 13 hearts and you're going to pick 5 of them. So that's the total number of hands of interest goes in the top of the fraction, and the total number of hands goes in the bottom of the fraction. So 13 choose 5 divided by 52 choose 5 is the chance of a flush in hearts. And of course there are 4 suits. So 4 suits times chance of a flush in any one suit gives you the answer. Let's go back to the command line, see if I can manage to type that in. Let's see, that was a 4 times binomial, what is that, 13 choose 5, all divided by binomial, 52 choose 5. And again, the system will just give me a fraction. It's certainly a much less scary fraction than the one before. I'll ask to look at what does the number look like by saying n. And you know, it's something like, can you see here, it's something like 2 1,000ths. So the chance of being dealt a flush in poker is 2 1,000ths. So getting into the possible range. Not likely, but possible range. Now, poker authors, if you have a poker book on the shelf, poker authors give the odds of such a hand, but they'll say that the chance of a flush is the chance of a flush minus the chance of a straight flush, kind of thing. We're not going to worry about that. That's a perfectly reasonable for a poker author to say, but we're just going to calculate the kind of most straightforward thing because I got people in the room who aren't too sure how to play poker. Never mind all this kind of fine stuff. Okay, now a straight consists of cards that can be put in a sequence. So for example, a 4 and a 5 and a 6 and a 7 and an 8 would be a straight. They don't all have to be the same suit. It could be 4 of hearts, 5 of clubs, 6 of hearts, 7 of diamonds, and 8 of clubs. That would be a perfectly fine straight. Okay, so how do you count the number of straights? So again, we're looking to put on the top of the fraction the total number of hands of interest, and on the bottom of the fraction the total number of hands. So the total number of hands is 52, choose 5. That part's fine. The top of the fraction is the total number of hands of interest, so we have to count the number of straights. I said aces are high, so I'm going to start with the lowest card. Then the lowest straight starts with a 2. Then the next straight starts with a 3, so 3, 4, 5, 6, 7 would be a straight that starts with 3. Then the straights that start with 4, then the straights that start with 5, all the way up to the straights that start with 10, and that's 9 possibilities. Now, the thing is that you can have all the different suits. So each possibility can have a variety of different suits. For example, for a straight that starts with a 2, the 2 could be any of the 4 possible suits. The 3 could be any of the 4 possible suits. The 4 could be any of the 4 possible suits. So there are 4 to the 5th many hands for each possibility. If I'm saying I have a straight that begins with a 3 and then has a 4 and a 5 and a 6 and a 7, how many such hands are there? Well, there are 4 possibilities for the 2, spades, hearts, clubs, diamonds. There are 4 possibilities for the 3, spades, hearts, clubs, diamonds, etc. So we're looking at a total of 9 possible straights. Each straight has 4 to the 5th possible variance in terms of suits, and all divided by 5, 52, choose 5. So I think this is going to be the last time I do this, but we're going to pop it down and calculate that. So I want I forgot already. 9 times 4 raised to the 5th, all divided by binomial 52, 5. And I'm going to stop pretending it's a fraction at this point and just ask for the numerical value. And there you go. You're looking at 3.5 thousandths. So it's about twice the chance of the prior one. A little less than twice the chance of the prior one. So what we're getting, of course, is a ranking of hands according to how likely or unlikely they are. And the ones that are less likely have more value. If you have a less likely hand than your opponent, then you win. A pair has 2 of the 5 cards in the same denomination, but no better than that. And again, I'm going to stop counting the chances at this point. So stop calculating the chances at this time. So we can have a pair of 2s, a pair of 3s, a pair of 4s, etc. So there are 13 possible pairs. For each possible pair, you have to pick 2 suits. So for each pair, let's say I have 2 3s. Now I have to pick 2 suits. Maybe it's clubs and spades. There are 4 suits. I'm going to pick 2. It doesn't matter whether it's spades and clubs or clubs and spades. So order doesn't matter, so I'm looking at 4, choose 2. So the total number of hands of interest here is 13 possible pairs. But wait a minute, for each pair there are 4 choose 2 possible hands with that pair. For example, 2 3s and then a clubs and a hearts. And then what about the remaining 3 cards? Well, the thing is, if you have a pair of 3s, then the remaining 3 cards can't be 3s. So there aren't 50 cards left here. There's actually only 48 because they can't be 3s. So 48, and then it's not 2 pairs, so it can't be the same. So if that's a 4, then this can't be a 4. So we're down to 44 and then 40. So that's the total number of hands of interest. You divide by 52, choose 5. And again, I'll stop with the calculating at this point. So excuse me, I'll stop with the calculating at this point. So we get that the pairs are a somewhat complicated expression. You have to kind of think through, why is it 48, why is it 44, why is it 40? And again, illustrating my point that counting is surprisingly hard, surprisingly intricate, maybe is the right word. All this stuff is elementary in the sense, for example, that you never have to take a limit, for example, but it's all pretty intricate, pretty tough to do. In the movie Good Will Hunting, if you've ever seen the movie Good Will Hunting, Matt Damon is supposed to be a genius, and his specialty is counting. He's a combinatorist. Okay, so now I want to turn to another aspect of counting. On the command line, I've been typing in binomial to say 52 choose 5. I type binomial 52 5, or to say 7 choose 2. I'd say binomial 7 2. So where's that come from? And the answer is here, of course. So this is basically high school math. I'm taking a plus b, for example, and squaring it. Here we go, a squared plus 2ab plus b squared. Here's a plus b cubed, and you just simply cube it. I mean, you take out a pencil and you cube it. You a plus b times a plus b times a plus b, and what do you get? You get a cubed, 3a squared b, 3ab squared b cubed. A plus b to the fourth, there you go. It goes, coefficient is 1, 4, 6, 4, 1. And a plus b to the fifth, the coefficients are 1, 5, 10, 10, 5, 1. So the question is, what's the formula? Obviously, there's a pattern. What's the pattern? Can we write the pattern down in some organized way? Can we give a formula? Okay, so the theorem is that if you want to figure out what is in the expansion of a plus b to the n, what is the term where the power of a is to the k, you take n, choose k. So what? So for example, if you're looking at a plus b to the fourth, so n is 4, and you want to look at the term that has a to the 3, so k is 3, then I'm looking at 4, choose 3. How many ways are there to reach into, a sack that contains pieces of paper numbered 1, 2, 3, and 4, and pick out 3 of them? And the answer, of course, is 4, because you could leave out the 1, you could leave out the 2, you could leave out the 3, or you could leave out the 4. So the term here that involves a to the k is n choose k. Of course, we need a proof for that, but the basic idea here is that you just simply you just simply want to say to yourself, how many a's, how many b's? If I type the terms here, a plus b, a plus b, a plus b, a plus b, that's a plus b to the fourth, and I say to myself, how do I get an a cubed b to the 1? And the answer is, in the a plus b, a plus b, a plus b, a plus b, I must have 3 times chosen an a. 1, 2, skip, and 3. And the other time was a b. How many ways are there to do that? Why, there are 4 choose 3 ways. In my case, I skipped the third one. Okay, so we're looking here at how many ways are there to choose 2 a's and 2 b's? There are 6 ways. Why? Well, because it's once I decide in the a plus b, a plus b, a plus b, a plus b, once I decide which of the 2 a plus b's I'm going to pick the a from, well, then the other 2 are automatically the b. So I'm looking at 4 choose 2, namely choose the a's. So what we have then is that a plus b to the nth power is a bunch of terms. You can see, for example, that the powers of a descend while the powers of b rise. So a bunch of terms, the coefficient of the term where a to the k is n choose k. Okay, so here's an example. Use the binomial theorem to expand 1 plus x to the n. Use the binomial theorem to expand 1 plus x to the n. I'm sorry, I hit the wrong button. There we go, and there we go. There we go. 1 plus x to the n. So in 1 plus x to the n, of course, the a is the role of a is being played by 1, and the role of b is being played by x. So let's take 1 plus x cubed, just as an example. Okay, so we're looking at 1 cubed plus. Remember how you do cubes? It goes, what? 1 cubed, and then it's going to go 1 squared x. Don't forget there'll be a term here. And then it'll go 1 x squared, and then it'll go x cubed. Okay, and what are the coefficients? What goes here, what goes here, what goes here, and what goes here? And the answer, of course, just from following the result, is there are 3 1s. So this is going to be 3 choose 3. Turns out that 3 choose 3 is the number 1, because if you reach into a bag that contains 3 things and you pull all 3, how many ways are there to do? There's only 1. This will be 3 choose 2. This will be 3 choose 1. And this will be, of course, 3 choose 0. So what you end up with is 1 times 1 cubed. 3 choose 2 is 3. 3x. 3 choose 1 is 3. 3x squared. 3 choose 0 is 1. Okay. In general, if we're looking at 1 plus x to the n, if we're looking at 1 plus x to the n, then we're looking at n choose n, and again that's the number 1, times 1 to the n, plus n choose n minus 1 times 1 to the n minus 1 times x, plus n choose n minus 2 times 1 to the n minus 2 times x squared, plus all the way down to n choose 0 times x to the n. Okay, so we get a long polynomial in x, and the coefficients are these n choose k, and that's where the phrase binomial arises that we use in Sage. Okay, there we go, hitting the button for the right time. So the Pascal's triangle is, I expect that everybody has seen the Pascal's triangle relation. Here it's on the next slide. Everybody has seen the Pascal's triangle relation, and we're looking, these are obviously the coefficients from the previous slide, the 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. The Pascal's triangle, and it has been my experience that most folks have seen before the pattern that just to pick an example here, let's look at this 10 here. You get the 10 by taking the 4 and the 6 and adding them. To take another one, this 15. To get this 15, you take the two numbers above, the 10 and the 5, and add them. To pick another one, this 6 right here. You take the two numbers above, the 1 and the 5, and add them. So this says to get the one thing in the next row, you take two things from the row before and add them. So n plus 1 choose k is n choose k minus 1 plus n choose k. And of course there's a proof. I copied the formula from the previous slide because I couldn't fit it all in one slide. And it's like many combinatorial proofs, it's just a question of having sort of the right insight. It's very short and easy to see if you have exactly the right picture. So maybe remember Matt Damon driving around Boston in the train, and he's looking out the window, he's trying to think of just the right picture to have. Maybe you didn't see the movie. Okay, so you consider a set that has n plus 1 elements because of this plus 1 up here. N plus 1 elements. The left side of the formula gives a number of ways to make an unordered choice of k many of these elements. So this is n plus 1 elements, make an unordered pick of k, of many of them. Now, here's the way to look at the right-hand side. You take one element to the set S and you color it red. So now S consists of n many elements that are not red and one element colored red. So each unordered selection in each unordered selection in the prior paragraph either does not have the red element or it does. The number of ways to avoid the red element is this. Since we are selecting from among the not red elements of S. You're selecting from among the not red elements of S. There are n not red elements in S, and you're picking k of them. Okay, so that's the number of ways to pick without picking the red element. This must be the number of ways to pick while picking the red element. And sure enough, that's what it says. You have decided you're going to pick the red element in the set capital S. So that means you're really only picking n things because you're already decided on the red element, so it's already done. So you're picking n things. How many things are you picking? Well, of course, once you've picked the red thing, it's already gone. So the things left to pick are k minus 1 many of them. So that's exactly what it said. With the red element put to one side, what you're actually doing is from among the remaining n things, you're picking k minus 1. And of course, you add the two together and you get the total. So one thing that illustrates is that there is a relationship among binomial coefficients, and in fact there are thousands of relationships among binomial coefficients, and they're very important for calculating the speed of algorithms, the resource use of algorithms. Knuth's, for example, art of computer programming, it seems like every time you turn the page you see relationships among binomial coefficients. It's just wonderful. But the classic one, the one that I'm going to show you, is this one here. And to show you that, I'm going to annoyingly go back. There we go, back. Please, here we use this to illustrate Pascal's triangle, but I want to illustrate something different now. I'm going to, instead of looking at the row below and the row above, I'm going to add across the rows. So 1 plus 1 makes 2. 1 plus 2 plus 1 makes 4. 1 plus 3 plus 3 plus 1 makes 8. surely a person is thinking now, so far, there's a 1, there's a 2, there's a 4, there's an 8. I think I get where this is going, and sure enough it is. 1 plus 4 plus 6 plus 4 plus 1 makes, well, 4 plus 6 is 10, and then 1 plus 4 plus 1, it makes a total of 16, and now you're not astonished to find 32, 64, etc. That when you add across the rows in Pascal's triangle, you get the powers of 2. Isn't that wonderful? Isn't that wonderful? And that's exactly what this theorem says. It says when you add across the rows, if you add across row n in Pascal's triangle, then you're looking at 2 to the end. Isn't that nice? And again, as with most combinatorial results, it seems like most combinatorial results, you have to have the right insight. And once you have the right insight, sometimes things click. It's a wonderful, wonderful thing. And the answer is, remember the binomial theorem. There it is. Take A to be 1 and B to be 1. So on the left-hand side, you're taking 1 plus 1 to the n. On the right-hand side, you've got 1s, 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 1s. All you're left is looking at the binomial coefficients. The left-hand side is 1 plus 1 to the n. That's 2 to the n, and you're done. Isn't that nice? Isn't that nice? Okay, one more topic. It's a combinatorial topic, but it stands a little bit aside from the previous combinatorial topics, and that is I want to look at how things combine when you combine sets with union. Okay, so everybody remembers, right, that A union B is going to be A plus B, take away, the size of A union B is going to be the size of A plus the size of B, take away the size of the intersection. So let me get my piece of paper back. Just flip that one upside down, and here we go. I'm looking at the size of A union B and if you imagine that A and B have some elements in them, looks like they have the measles. If A and B have some elements in them, if you wanted to count the total number of elements, you would of course count the number of elements in A plus the number of elements in B. But wait a minute, you've counted the overlap twice. You made a mistake and counted the overlap twice. So you need to subtract away one of those counts. Let's try it with 3, which is really the bigger point. I'm trying to make it big enough so that a person can see. Hope that's big enough. Okay, and of course here again we're looking at A, B, and C. And again we're imagining that there are some elements in there. Okay, I'm going to try to count total number of dots. So I'll count the number of dots in A, and the number of dots in B, and the number of dots in C. But again, I've overcounted because some of the dots, for example, these 2 dots here got counted twice. These 2 dots here got counted twice. These 3 dots here got counted twice. So I'd better subtract away to make sure that I'm not double counting things. So I double counted the things in the union of A and in the intersection of A and B. And I double counted the things in the intersection of A and C. Right, those 2 dots there got double counted, once for A and once for C. And I also double counted the things in the intersection of B and C. Oh, I fell off the side of the page, I'm sorry. But wait, look at these ones right here all the way in the middle. That dot all the way in the middle got counted. So in fact, got triple counted. And then subtracted. It got uncounted 3 times. So we're down to counting 0, a net of 0. So I've got to add back A intersection B intersection C, all the things in there. So there's this add, take away, add, and there's at least some sort of general pattern established. So what we've got then is add, take away, add back, and in general the union is you do the adds, the takeaways, the add back, and you add all the singles, you subtract all the doubles, you add all the triples, you subtract all the 4s, add all the 5s, etc. if there are 4s and 5s. Here's the 4 case. The 4 case is derived from the 3 case by first you write down here A1 union A2, union A3, union A4, you consider that to be the union of this first thing, this in parentheses, this triple, union with A4, and we know from the first line on the prior slide that that is number of things in the first plus the number of things in the second. Subtract the intersection. And now we know how to count the number of things in the first. It is add the singles, subtract the doubles, add the triples. And don't forget here that on that line I have the size of 8 to the fourth. And now then I'm subtracting away here what is the size of this intersection. De Morgan's law gives you that the intersection, it's getting so complicated, but it works out. There is the sum of the singles. Do you remember the single over there? There's the sum of the singles. There's the subtract the pairs, and there's the add on the triples, and subtract, and subtract the 4, so all the way. See the minus sign? Subtract the 4. So let me go back to my paper and write it out in some more organized fashion. Oh, these buttons, so many buttons. There we go, and there we go. Ah, there we go. Okay. Okay. So if we're looking to take 4 things, so we're looking for the size of A1 union A2 union A3 union A4. And it's going to be complicated, so I'll leave a lot of room. First of all, you add the singles. Then you subtract the pairs, and there's going to be a lot of pairs. So let's see, A1 intersect A2, A1 intersect A3, A1 intersect A4. That's all the A1s. And then A2 intersect A3, A2 intersect A4, and finally A3 intersect A4. Okay. This, of course, is, I'm looking here at, right, I'm looking at 4 things and choosing 2 of them at a time. Anyway, adding in the triples. So adding in the triples is leaving 1 out. So first I'll leave out A4. Leave out A3. And leave out A2. I'll write that on the next line. And finally leave out A1. A2 intersect A3 intersect A4. Okay? I told you it's going to be a mess. And then finally the last is, so I added, I subtracted, I added, and now I subtract the intersection of them all. Okay. So complicated, not brutal, but complicated. Okay. Okay, very good. So that's the, I'm not going to do the topic from the section, but so that's the, that's all of the counting that we're going to do, and counting proves again to be elementary in the sense that it doesn't use any limits or any advanced material like that, but surprisingly intricate. Okay. Okay, very good.